In this video, we're going to have a look at how we can calculate the equations of lines that describe both the tangent and the normal to functions at any given value of x. In this particular case, we're going to have a look at how we can do the tangent and the normal function to the function f of x equals x squared plus 2 at the location of x equals 1. So to do this, it's simply just following a simple process. It's a 5-step process that will take us from not having a line to having the equation of a line that describes a tangent and normal. So the 5 stages there, they're quite simple. Firstly, we simply calculate the derivative of the function f of x. Then after we've calculated that, we look at the location, or we calculate the point where the tangent is going to touch the function f of x. So in most cases, if you're given the value of x, it's simply a case of calculating the value of y. Thirdly, we're going to compute the slope of the tangent at said point. So if we're given the value of x, it's simply a matter of plugging that value into the derivative of the function f of x. That will tell us that slope. And then finally, in section 4 or step 4, you simply find the y-intercept. So this is stuff that you're doing in topic 1 of semester 1. So you've got y equals mx plus c, you've got a point, you've got a slope, calculate the value of c. And I said finally in step 4 because in step 5 it's really just rewriting out what you've already done in 1 to 4. So it's not too complicated, but it can be a little bit daunting if this is the first time you're doing this. So jumping straight into it, we've got the function x squared, or f of x equals x squared plus 2. Well, firstly, what does this even look like? So if I quickly do a rough sketch, what we're going to find is that our function, if I draw some axes, that will have to do. Our function itself, it's an order 2, and it's a parabola. So, and it cuts at plus 2. So what we're going to find is the function looks something like that. And if we're looking for the tangent, well, if we say x equals 1 here, then what we're going to find is that we're looking for a line, the equation of a line that looks something like this. So y equals mx plus c, and this guy here equals f of x. So we're looking for the line that touches at x equals 1, and we're looking for this equation there. So first thing we need to do is we need to find the derivative of f of x. So f of x equals x squared plus 2. Now, we could go 2 ways. We can use a simple power rule, or we can use first principles. In this case, the question just says find the derivative. So in fact, it doesn't even. It just tells us to find the tangent and normal. So I'm going to take the path of least resistance, and I'll use the simple power rule because it's just easy. So we'll go 2x and we're done. Alright, cool. Now second step, we need to find the point. So we need to find that point right there. So where the tangent itself touches our function, we're told it's at x equals 1, so therefore we need to find the value of the y, or the y value. So we're going to go f of x equals x squared plus 2, and then it's at x equals 1, so f of 1 is going to be 1 squared plus 2, and therefore 3. So this point here, it's at 1 and 3. That's where our tangent touches our function. Now going down to step 3, we're going to find the gradient. So what is this value of m here? Well, if we know that f dash of x explains the gradient of the function for any given value of x, then it's simply a case of substitute in 1 in place of x. So 2 times 1, and therefore that is simply equal to 2. Too easy. Moving down to part 4, we need to find the value of c. So this is where it gets a little bit involved. Remember, if we're going for, say, y equals mx plus c, remember that the values of y and c are explained by the point 1 and 3, and the value of m, let's get a thicker pen, the value of m here is explained by f dash of 1, and we've already calculated these. So if we rearrange to solve for c, what we're going to find is we get c equals y take mx, and we've already got y and x. So if I quickly rewrite it in its form or notation we've been using here, it's simply c equals f of x minus f dash of x times x itself, and in this case x equals 1. So x equals 1, so therefore f of 1 minus f dash of 1 times 1, f of 1 is simply this guy here, 3, take f dash of 1, that's going to be 2 times 1, and therefore the value of c is simply equal to 1. So therefore, putting it all together, we're going to get this line here is explained by the equation y equals, and our gradient was, what did we say? The gradient was equal to 2x plus 1. Awesome. Now going over to Desmos to verify what we've just done. So our function itself was defined as f of x equals x squared plus 2. So this is our function. Our derivative function is equal to over dx. So Desmos will do the derivatives for us, which is really nice, like so. And notice that it's come out and it looks completely different. So keep note, this blue function here, it's not the tangent, but rather it's a function that tells us the slope for any given value of x for its original function here. So we'll turn that off because we don't need to see that. Now going down, we're looking at a point. So where does our tangent touch our function? So I'm going to go, it touches at location A and f of A, where location A is at 1. So here, whoops. Here is where we're looking for the tangent, so location 1, 3. Alright, awesome. Now we have to go for the line. So we're going to go y equals mx plus c. And remember, the value of m in this case is simply going to be the derivative at location 1. Awesome. And it's already put it in here just by coincidence, but we have to now calculate the value of c, because otherwise we've got a line and it's got the right slope, but it's not touching our function where it should touch it. So I'm going to put that in using our form that we saw over here. So c equals f of x minus f dash of x times x. Putting that in, we're going to go f of a minus f dash of a times a. Now what you can see is we've got this beautiful looking tangent to our original function here, our parabolic function, and because it's in a general case here, we can actually move it around and see how our tangent moves for any given value of x. Alright, cool. So this is the process we use to get the tangent to a function. Now let's have a look at how we do the normal to a function. The normal being, well, if our tangent looks like that, then our normal is going to look like that. And let's just assume that those are 90-degree angles there. So the normal to a function or to a line cuts at 90 degrees. Alright, so I'll do this one in a different pen, just for a bit of clarity. So for our normal, we're going to repeat from step, we'll go back to step 3. So calculate the tangent. Well, in this case, we're not calculating the slope of the tangent, we're calculating the slope of the normal. So the normal. And then, because we're getting a different slope, we're going to have a different y-intercept, and then once you do that, you just plug it all back in together. So doing that, we're going to get, so our, go question 3, or part 3, if f dash of 1 equals 2, and this is our tangent, then for the normal, we're going to go, we'll say n equals -1 over f dash of 1, and that will become -1 over 2, and then our normal is simply -0.5, like so. Now using step 4, where we've got the c, value of c equals f dash of 1, take 1 over, -1 over f dash of 1 times 1, and recall that this in here, this is our normal. It's our normal represented there. So with all of that, we're going to get 3 take, this will become -0.5 times 1, and then it will become simply 3.5. So bringing it all together in 5, the equation, so let's see why the equation that describes the normal to the function for x, or any given value of x, is going to be, or at x equals 1, is simply going to be, where is it, our normal is -0.5 x plus 3.5, like so. Now if we go over to Desmos and key this in, then what we're going to find is we'll go y equals, and we'll go y2 equals nx plus c2, where n is going to be represented as a normal. Well, in this case, it's simply -1 over that, and then the value of c is simply going to be the same as above, except rather than going like so, we'll go like so. So have a look. For any given value of x, we get the normal represented in the green line and the tangent represented by that black line. So this has been a video on how we calculate the tangent and the normal for any given values of x. In the next video, we'll have a look at doing it for a cubic function.